So in part A, we have a square root of 5 in the denominator, and we want to get rid of that square root of 5. And the way we do that is we multiply top and bottom in such a way that there's no more square root of 5 downstairs. Since that's a square root, we would need to make it a perfect perfect square. So to make it a perfect square, we're going to multiply top and bottom by the square root of 5. By multiplying top and bottom by the same thing, we're essentially just multiplying by 1. So we're not changing the value of the number, we're just changing what it looks like. So upstairs we have 7 times square root of 5, which is just that, 7 square roots of 5. Downstairs you can skip this step if you want to. Square root of 5 times the square root of 5 is the square root of 25 because of the product rule. And what is the square root of 25? So our final answer is 7 square roots of 5 over 5. So our initial problem and our answer in the box are the exact same decimal value, but the one in the box no longer has a square root in the denominator. We want to get a perfect square in the denominator because we have a square root. So just like before, we're going to multiply top and bottom by the square root of 5x. So we'll talk about the real reason this works once we hit part C. So no, they're not going to be this nice. Upstairs, you have 18x times the square root of 5x. Those just are put next to each other. Downstairs, you have the square root of 5x times the square root of 5x. What is that? So you could say square root of 25x squared, but then how does that clean up? We're going to assume that the variables represent positive numbers, so no absolute values here. Just 5x. But unlike part A, we have some cleaning to do. What cleans up now? The x's. Can I reduce the 5's? No. The 1 5 is underneath the radical, the other 5 is outside. So in part A and part B, we had to make perfect squares. In part C, we have to make a perfect cube. So notice, if we tried the same technique of just multiplying by whatever the denominator is, then downstairs, cube root of 6 times the cube root of 6 is the cube root of 6 squared. What is the cube root of 6 squared? Nope. It's cube root of 6 squared. It does not clean up, because 3 doesn't go into 2. So this is not good. So when you're rationalizing, you can't just multiply by whatever the denominator is and call it a day. What you have to do is subtract. What is the exponent on the 6? 1. What is the index of the radical? 3. How many more do we need? 3 minus 1 means we need 2 more. So we're going to multiply top and bottom by the cube root of 6 squared. Upstairs, we get 2 times the cube root of 6 squared, which we'll clean up in the next step. Downstairs, thanks to the product rule, since we have the same index, we can multiply the radicands. What is 6 times 6 squared? What is 6 times 6 squared? 6 cubed. Well, what is the cube root of 6 cubed? 6. So we needed to make a perfect cube. We only had 1 6. We needed 2 more to make a perfect cube. Upstairs, let's clean up this radicand. What is 6 squared? 36. Let's go back to the other ones and talk about why it worked. So the index on both of these were 2's. And here we had 1, 5. So 2 minus 1 makes 1, which means we need 1 more. Whatever I multiplied downstairs, I also have to multiply 1 upstairs. Here again, we had a 2. We had 1, 5, and 1 x, which means we need another 5 and another x. Sure. So for C, we need to make a perfect cube. So I need to make this radicand 6 cubed. I currently have 1, 6. I need 3. How many more do I need? 2. That's where this comes in. Because when you multiply two things to the same base, what do you do to the exponents? So 1 plus 2 makes a 3. But whatever I multiply downstairs, I also have to multiply upstairs. Well, downstairs I got my cube root of 6 cubed. Cube root of 6 cubed reduces to 6. This 6 squared becomes 36.